All right, final session of our third week of remote learning. This is being recorded, so if you are here presently or if you are tuning in later, welcome, welcome. Spring break next week, so we got a lot of good things coming up. All right, so happy Thursday. Let's go over the announcements again real quick. Ed puzzles and assignments due this Friday, aka due tomorrow. Let's specifically go and tackle which ones are due tomorrow. Notice anything with the recommended due date of 4/3, that is what is due tomorrow, because tomorrow is April 3rd. And so that's going to be basically all of the lessons of this unit, 14, 15, 17, 18, and then the quizzes, because the quizzes is taking place of lesson 19. Kind of notice that right here. Log quizzes right there. All the ed puzzles, I've been grading those. I've been turning them in with scores based on correct or incorrect, but keep in mind that the ed puzzles are classwork. They're being done for completion. Effectively tomorrow afternoon, what I'll do is I'll go and I'll record everyone who has completed the ed puzzle, and I'll go enter a score in for you doing that into Infinite Campus. So please try to get those ed puzzles done as well. If you have any questions, as always, continue to fill out our remote learning questionnaire. This thing right here. Okay, I kind of opened it up for this entire week. I didn't post a new one. It's just the same document. So the 5 of you that posted on Tuesday, I got back to you already, I believe. So continue to ask me questions on that or via email. Sweet. Okay, so all of that due tomorrow. The fact that we are remote learning, I will be lenient in terms of collection and grading. So if you do need an extension, reach out to me, let me know, and I'll get that done for you. Remote learning agenda, use the new one. We talked about this on Tuesday. I just want to reiterate it again, kind of starting off our class with our announcements here. That's this thing. This is our pace and what we're doing in the class each day and what is expected of us in terms of our virtual resources and our assignments. Notice that today's agenda, April 2nd, it's crazy, already more than a fourth of the way through the year. Now that we're in the 4th month. Today we're going over a review, so I'm not going to spend too much time on this agenda. I want to jump right into that. We're going to go over some of the comprehensive review assignment, and we'll also go over one problem in lesson 19, a word problem. All right, so use this as your pacing, as your guide to the rest of this class this year, at least through this comprehensive review assignment. We'll do one or two of those problems today. Due 4/17. This is kind of the big assessment for this unit since we're not having a direct test due to remote learning. So that is due on the 17th. Do your best. You can go back and edit or resubmit. I've had 3 people turn it in already. Very well done. Y'all didn't get 100s on it yet. No big deal. I want you to go back in, edit, or resubmit if you so desire. And now the spring break is next week, so hopefully you enjoy your time doing that. Hopefully next time we meet, which will be 2 weeks from yesterday, you'll have some good stories of something that you've done, even if you're just staying at home, finding some projects to do. All right, cool. So today's whole goal is to review the entire unit on logarithms, which kind of double down and build off our exponential functions. Really today and the comprehensive review assignment, these lessons and assignments are going to be combining all of those knowledge and skills into one kind of assignment that we call the CRA. All right then, without any further ado, if you don't have any questions, please, if you do have any questions, please let me know. And right now, and if not, also, before I move into that, I'm going to start taking kind of a flexible attendance here just because numbers are kind of low on participation, or at least in terms of engagement. So if you are here right now, please type into the chat box here, and moving forward, start to get some sort of use that to our advantage here. So again, if you are here and looks like there are 14 of you, please type into the chat box that you are here, and then I'll get that noted later on after I close this off this afternoon. Right on, cool. All right, again, anytime if you are here, just let me know that you are here. All right, cool. Let's move into today's lesson then. First things first, I want to start off on page 259. We're going to do problem number 12. Keep in mind, y'all, that last class on Tuesday, we did problem number 11. This behemoth right there, yeah, and did that whole problem. It took a lot of space, so I actually opened up a new file to do number 12 because I ran out of room due to the work that it took to do problem number 11. But we are still sticking basically where we left off with, and that is on page 259, problem number 12. We're going to do this problem first, and then I'm going to try to get at least 2 problems done in our CRA, okay, our comprehensive review assignment. So chain emails contain a message suggestion that you'll have bad luck if you do not forward the email to others. I'm sure we've all seen this. A lot of times I personally spam these things. A lot of things on Facebook do this as well. But suppose that a student started the email by sending 10 messages or a message to 10 friends and asking those friends to forward that email to 3 people, 3 more friends exactly 1 day after receiving the message. Okay, I know I'm kind of butchering reading this problem because we have our function already lined up beneath us. E of n equals 10 times 3 to the n power. So basically, I kind of used highlighting here in colors here to denote where these numbers came from. 10 is the starting value. That's kind of our y-intercept, if we want to call it that. It's where we begin. And that base of 3 tells us how many people we're sending that message to each day. And they tell us that n is the nth day, so n is the number of days there. So my first question before we actually even get to what number 12 is asking us is, what does E of n represent if n is the number of days since the first email? Well, E of n is the number of emails. So effectively what we're looking to do by working with this multicolored function now is we're trying to figure out the number of emails if we started with 10, sending it to 10 people, and we asked those people to send it to 3 more people each and every day thereafter. Again, keeping in mind that if you send it to 3 people, and they send it to 3 people, and they send it to 3 people, then it's going to be exponential in growth, multiplying by 3 every single day thereafter. Hence why we have an exponent in our function, and thus why we're working with our exponential functions here, kind of wrapping up this unit. So the first thing that we're asked to do is to assume the population of the United States is 318 million, and everyone receives the email sent to 3 people who have not gotten it previously. We want to figure out how many days it would take to have the email sent to everyone. Effectively, we're looking for, in this problem, part A, is we're solving for the number of days, or we're solving for n. So here's what we know. We know that E sub n is the number of emails sent. So if we're trying to send an email to every single person in the US, hypothetically, we want to send it to 318 million people. So I already kind of wrote out the equation down here. Sorry, let me zoom out a little bit, just for sake of time, because it's kind of hard to write on this thing really quickly. So I wrote out this equation down here to represent the situation. Now, I wrote it out in 2 different ways. The way on the left, got a laser pointer set up, gives us 318 million in straight numerical form, and the way on the right gives us kind of a scientific notation. Effectively, what I did is I took the number of zeros after the number 318, 1, 2, 3, 4, 5, 6 zeros. Sorry, let me get that off the screen. And I took those 6 zeros and turned it into 10 to the 6th. Same equations, just one deals with a base 10 situation, and we could use this to our advantage. I'm actually going to focus on the left one though. So although I gave us 2 equations, I'm going to actually now erase one of them. I just wanted to mention that it's possible. All right, so here's our situation. We have 318 million people. We start off by sending it to 10, and then they send it to 3 more people thereafter, where n is the number of days, and that's actually what we're looking for here. So we have our equation from the information. Now all we have to do is solve for it. So we know our unknown is buried up in the exponent, so we might have to use a logarithm at some point. But the very first thing that I'm going to do is I'm going to start to work to isolate the unknown by dividing both sides by 10. Because now what I have is 318 million divided by 10 is just basically saying take away one of those zeros. So I have 318 with now 5 zeros after it, or 31 million. My commas didn't do a very good job there, sorry. 31,800,000 is now equal to 3 to the n power. Trying to keep my colors close here. Okay, so now after dividing by 10, we're getting closer to isolating our variable. Our goal here, right on. We now know our variable is buried up in the exponent, so we're going to have to utilize our logs now. I'm going to log both sides. So the log of 31,800,000 is equal to, if you log one side, property of equality states that you got to do the same thing to both sides, log 3 to the n. Now what we have done here is we have opened up the ability, I'm going to kind of cruise over to the right side now, is that we have opened up the ability to use our properties of logarithms. 31,800,000. And the properties of logarithms specifically deals with this part right here. And it states that if you have a power of an argument, and we do, 3 is being raised to the n power, then we could drop that down in front. So that's what we're going to actually write right up here, that we take that log 3 to the n and we rewrite it as n to the log of 3, or n times the log of 3. Right on. So now there's one last thing we have to do, and that's to isolate n. And since n is being multiplied by log of 3, keeping in mind log of 3 is just a calculator function at this point, just a number, 10 to what power equals 3. To get rid of multiplication, we just use the inverse. We divide both sides by log of 3. And then we actually know exactly what n is equal to as a quotient of this mondo thing right here. Boom. Okay, so now all we got to do is use our calculator to our advantage, take the log. And notice once we kind of realized the change of base formula and our properties of logarithms, we were able to rely on our calculator and making anything that's in an exponent solvable, or any unknown that's an exponent solvable. And that's what we've really been practicing the last few days. So we have the log of 31,800,000, right on. And then we're dividing that whole thing by the log of 3, I believe it was. That's right. And now we have our solution where n is about 15.7. Take that whole division problem, simplify it down, evaluate it, kind of use the common math term. N is 15.7, and that is going to be in terms of days. Remember, n was number of days that we were sending these emails out. So, which is pretty crazy if you think about it. Theoretically speaking, if you sent an email to 10 people and you asked them to forward it to 3 other people every single day, and again, this is theoretically because getting it to 3 other people who haven't received the email before would be very difficult. But eventually, just under 16 days, every single person in the United States at the 3 every day would get that email, which is pretty crazy to think that it grew from 10 to 318 million in just under 16 days, just over 2 weeks. Right on. Same thing would be done, by the way, for part B, except for now the only thing that's changing is our E sub n. It's now 7,100,000,000. So now we're talking about to not just everyone in the US, but everyone in the earth. So we would divide both sides by 10, log both sides, and do the same thing there as well. But for sake of time, we're going to actually cruise into our comprehensive review assignment and not go through the same process for part B, because it is the same thing. E sub n. Right on. If you have any questions, please right now either unmute yourself and ask, or raise your hand up, or type it into the chat box, and I'd be happy to answer that before we move into our comprehensive review assignment. Also, if you have started or looked at the CRA and you want me to kind of tackle a specific question for you, please let me know right now and I'd be happy to do so. If not, I'll just kind of go over a couple of ones that I want to specifically talk about. Any questions? All right, cool. By the way, for the 17 of you that are in here, again, if you haven't already typed the word here into the chat box, please do so to let me know that you are here for attendance purposes. I'd much appreciate that. All right. So here's the CRA, Comprehensive Review Assignment, accessible through the Google Classroom. As we know, all of our classwork and our assignments are. This is kind of the heavy hitting one. It is by far worth the most because it is, as the title suggests, which means covering everything, and it's a review assignment. So please make sure you give this your full and undivided effort and attention. It is due 2 weeks from tomorrow, okay? All right, so this is what it looks like. 1 problem, 2 problems, 3, 4, 5, and 6 problems right here, right on. Okay, so we have 6 total problems in the comprehensive review assignment. Since I haven't gotten any this, I want to go over number 2 first. And we want to solve this logarithmic equation. And this logarithmic equation is log base 6 of the argument x minus 7 plus log base 6 of the argument x plus 2 is equal to 2. So let me get rid of this purple box around it. So a couple of things that stand out to me right here. One, these logs have the same bases. Now they're not common logs or natural logs, base of 10 or base of E, but they are common bases, which is awesome because that is going to allow us to execute or really highlight the second big thing that stepped out to me, and that was that I'm adding these common base logs. So what I mean by to me there is that this addition problem says that I can use a property of logarithms. And that property of logarithms we called the product property. And the product property of logarithms is a fancy title to say that when you have two logarithms with the same base, and we do, then we can separate the factors of that argument into an addition problem, or conversely, meaning in reverse, in this situation, since we have two logs with the same base, we can move opposite and take this addition problem and multiply the arguments as factors. So what that means in actual visual form is that since we do have these same bases, let me get that purple back up there, then I can take these arguments, x minus 7 and x plus 2, and treat them as factors, thus multiply them together. So the product property logarithm states that I can do the following. I can take my log with a base of 6, and I can take those two arguments, x minus 7 and x plus 2, and multiply them together because we have that common base log and because we are adding those two common base logs. Kind of a reverse process of the product property as we originally learned it in class. Right on. So now what we've done is we've turned this into a single logarithmic equation, which means we can translate it to an exponential equation and then solve for x. So let's do that. Let's translate it. Translation says log with a base of 6. So our base is 6. The answer to a logarithm, aka what a log is equal to, in this case 2, is always the exponent. So 6 to the second power, base of 6, answer to log exponent, right on, is equal to the argument itself. And for sake of time, I'm just going to copy and paste our argument, which you notice we haven't actually evaluated or simplified yet. Whoa, I don't know what just happened there. My computer freaked out at me, something I did wrong. Okay. Sorry about that. Okay. Again, we haven't evaluated this argument yet, but now it doesn't want to let me copy and paste. So what I'm going to do is I'm just going to write it. That's what I get for being lazy. Okay. Again, time because I ran into some technical difficulties here, y'all. Base of 6, base of an exponent, what the exponent sits on. Answer to a log is the exponent. Boom. And it's asking, it's being equal to what the argument is. And again, our argument is this set of binomials, these green binomials being multiplied by themselves. So let's work this down. 6 squared is 36. Nice. Let's use our double distribution, aka FOIL, to work this down. X times x is x squared. X times 2 is 2x. Negative 7 times x is negative 7x. And last but not least, negative 7 times 2 is negative 14. Right on. Now we have a more conducive problem to solve because this is a quadratic, a power of 2. And we know that anytime we have a quadratic, our end game, our goal is going to be to find its zeros. Okay, set it equal to 0, which I'll do in my next step after I combine my like terms. So 2x minus 7x is 5x. We still have that negative 14 that's coming along for the ride. Okay, so I've kind of cruised through this pretty quick and disjointedly due to the technical difficulties, but effectively what we did is we used the property to multiply those two green binomials, our arguments, and then we turned that into an exponential equation. And now there's a lot of colors and movement going on in this problem so far, but effectively what I've been doing is I've been simplifying down each side through multiplication and exponents. Then I combined my like terms. 2x minus 7x is negative 5x. Now, as I was saying while I was originally doing this work, since we know this is a quadratic, a power of 2, we always look for the zeros. Therefore, this thing is not currently equal to 0, so let's set it equal to 0 by subtracting 36 from both sides. And now, sure enough, this quadratic is legitimately equal to 0, as we can see right here. And when we subtract negative 14 minus 36, we get negative 50. So now there's a variety of ways that we could solve this quadratic. Graph it, don't want to do that. Completing the square totally works, applicable, don't really want to do it personally. Factoring, always my favorite, and or the quadratic formula always works. I like to preset with factoring, so let's try to do factoring first. AKA, what number in front, first times last? What are the factors if we talk about this X method? Just a quick review of something we've done a lot this year. Factors of negative 50 that sum up to negative 5, and the factors of negative 50 that sum up to negative 5 are negative 10 and positive 5. And now we can use our shortcut since our leading coefficient is 1 and say, all right, X and negative 10 and X and positive 5. At this point, zero product property states we could set these factors individually equal to 0. And then solve. Add x equals 10, subtract 5 from both sides, 0 minus 5, x equals negative 5. Boom. Problem number 2 done. So real quick recap. We used our product property. We multiplied the arguments, the greens. We set it up into an exponential equation. So that way we could use old school tactics of algebra to help us, including our knowledge of quadratics, which we eventually got to. Once we evaluated with that exponential equation, we got down to this highlighted problem here. We combined like terms. We realized that it was a quadratic. So then what did we do? We set it equal to 0 by subtracting 36. And then I decided to go with factoring this quadratic, used our X tactic over here. First times last, factors that gave us the middle. Get all this color off here. And then set the factors equal to 0, zero product property, saying if you have a multiplication problem, it's the best case scenario because we have to find or set the factors equal to 0, which we did there in purple, got our 2 solutions. All right. Any other questions or any questions on this problem? I know it's kind of a lot of information to digest, so if you are here present or if you're watching this video, go back and pause as you need accordingly. If you're present and you couldn't get this all down and you don't want to ask right now, always feel free to go back and reference this video on our YouTube channel and pause and rewatch it, okay? All right then, with the time that we have remaining, I'm gonna do the next one. And I want to do the next one because it's specifically pertinent, meaning related to all the things that we've done in the last 2 units, logs and exponents. It's going to be similar in form to the one that we originally did on page 259, number 12, but it's obviously a little bit different because now we're not talking about chain emails, we're talking about cash money. Okay, so in this case, we want to invest $2,000 into an account that earned 4.75 compounded continuously. Excuse me, that's huge, because that's going to dictate which formula we use. And we want to figure out how long, AKA, when I see how long in a problem, especially that deals with money, I think I'm looking for time, variable T, which I'll call it. So we put $2,000 into account, earning 4.75% compounded continuously. We want to figure out time, and we want it to grow to $5,500. So the compounded continuous formula or continuously compounded interest formula that we learned was A equals P times E to the RT, colloquially referred to as. Now we can fill out what we know. All right, we are looking for time. That's like legitimately what we're solving for. So I'm going to write that in blue. That's our unknown, which means we should know every other piece of this puzzle. We should know A, P, and R, keeping in mind E is just a constant, about 2.71. It's our constant for continuous growth rate. So we'll use a calculator to our advantage there. But do we know what A is? A is the ending amount. We sure do, 5,500. So our ending amount that we want our investment to be at the end, 5,500. Do we know principal, starting amount? Yep, our principal was $2,000. We invested that $2,000 and we want it to grow to $5,500. Oops, I don't know where my second 2 came from there, I'm sorry. And then our rate of return in this case is going to be, let's use orange, 4.75%, but 4.75% written as a workable form as a decimal is 0.0475. We get that by taking 4.75% and turning it into a hundredth place by moving the decimal 2 places to the left. All right, crushing this problem. And again, we got this from our formula, which I am going to rewrite right now. A equals P times E to the RT, and then all we did is we plugged in our applicable unknowns. Now at this point, we have our equation, and our unknown is in the exponent up here. Don't like that. So what I'm going to do is I'm going to work backwards, use opposites and logarithms now to extract that t from the exponent. So let's get this process done. Divide both sides by what's being multiplied by, and that's what it's being multiplied by is 2 grand. So I'm going to divide both sides by 2 grand right off the bat. 2 grand divided by 2 grand gives us e to the 0.0475 times t. Right on. Move this up a little bit here, okay? And then when we divide 5,500 by 2 grand, just 55 divided by 20 would be 11/4, or 2.75. Okay, cool. So once we did 5,500 divided by 2 grand, we are now down to this close or more isolated problem, which is looking good at this point. Now all we have to do is log both sides to extract that t out of the exponent. But it just so happens that I have a specific logarithm here. I have a natural logarithm possibility, because natural logs, or ln, is really just log with a base of e. So to extract something out of an base with e, we can use natural logarithms. So all that's to say that I'm going to now take this equation and I'm going to ln both sides. Now, when I ln both sides, what I've really done here is I have effectively canceled out this ln of e, and I have brought down this exponent like such. And another way of thinking about it is effectively the power property states that when you raise an argument to a power, you could bring it down in front. And what the ln of e is, the ln of e, that whole thing right here, is 1, because it's saying e to what power is e, and that's e to the first power. So really, what we've done is we have, by lning e, we have taken out the exponent right on, and now it's still equal to the ln of 2.75. We are almost done. All we have to do now to isolate t is divide by the decimal, 0.0475, at which point we are going to have a straight up calculator problem to finish off. That t, now isolated, boom, is equal to something that I'm definitely going to plug into a calculator. That t, now isolated, is equal to this calculator problem. For some reason, my fingers today aren't working as well as I would have hoped to have, so here we go. Sorry about the delay. And now all I got to do is plug this problem into a calc, which is where we're going to finish here. Natural log function, ln of 2.75. My goodness. What in goodness name? Okay, sorry about that, y'all. Divided by 0.0475, there's our 4.75%. And how long would it take? Let's round it to the nearest tenth, 21.2968 to the nearest tenth place is going to be about 21.3. Therefore, it's going to take 21.3 years for that 2 grand to mature into 5,500. All right, that effectively takes us up through the end of our lesson today, which is going to take us up to the last session we have before spring break. I know it's not necessarily as ideal of a spring break as we originally thought it would be based on the fact that we're staying at home. But again, I do hope y'all are being safe, healthy, doing your homework and all your classes, but also keeping time to find enjoyment with yourselves and those projects that aren't related to work as well. Keep in mind, y'all, next week is spring break, okay? You are more than welcome to do schoolwork during it, but take that time to rest and relax, to let your brain kind of unwind from all the craziness that is math, all right? So you're welcome to do math work during it. I'll be home, I'll be able to answer questions, but I also want to empower you to kind of take a break and not do any math, all right? On that note, unless you have any other questions, I want to say goodbye for today. And I do appreciate y'all being here as always. Miss you, and I'll see you 2 weeks from Tuesday, meaning the, gosh, what is it? Today's the 2nd, I don't know, probably the 8th. Yeah, that sounds right. Okay, on that note, or maybe the 10th. Anyways, have a great day, have fun, be safe. I'll see you in a couple weeks. Bye, y'all.